So up to now, we have seen how to write a function like the function sum that takes a list as an input and calculates an integer as output. Right now, we can go beyond this and define a function that outputs a list, not just an integer. This will not be so difficult. We will use pattern matching and recursion as before, but the output will also be a list. And we will use as example the append function that you've seen before, which concatenates two lists. There will be a special point that we will notice, though, in this example, is that this simple append function that we will write will automatically be tail recursive. This would be kind of surprising, since naively we might think that the output list is created after the recursive call. But this is not true. The output list is created before doing the recursive call. And we will see this by translating append into the kernel language of the functional paradigm. So this is the first time we are going to use the kernel language in order to help us understand the execution of a program. So this translation into kernel language will show us that the recursive call of the append is in fact the last call in the function body, and it will also show us that it's possible because of single assignment. So single assignment means that we can create the output list, which is an unbound variable, before doing the recursive call, and it will be bound in the recursive call. And this is a crucial advantage that we get from single assignment. It's the first of several important advantages that we will get from single assignment. Remember, single assignment seemed like a handicap when we first introduced it, but now we will start getting dividends from the price we paid up front. So the first dividend we will get is that simple list functions will be tail recursive. But that's not the main dividend. The main dividend will come when we introduce deterministic data flow, but that will be done later. So remember from lesson 1, the kernel language is the simple core language of a programming paradigm. And at this point, we have enough concepts to introduce the kernel language of the functional paradigm. In fact, all programs in the functional paradigm can be translated into the kernel language. And there is a simple principle that underlies this translation, which is here in blue. All intermediate results of calculations must become visible, and they're made visible through new identifiers that are introduced in the program. So that's the main principle of this translation. And this means that all functions become procedures with an extra argument that corresponds to the output, and all nested expressions, function calls, will be unnested, and identifiers will be introduced so that we see all the intermediate results. So the kernel language is actually the first of the two parts of the formal semantics of a programming language. So it's already half of the semantics in some sense. The second part, which is the abstract machine, which is a kind of a mathematical mechanism that shows the execution, that second part we will see in lesson 6. So right now, we can already see the first part and get some advantage, some extra understanding from this. So here it is, the kernel language of the functional paradigm. It's almost complete. There's only a little bit that has to be added. In fact, in lesson 4, we will make it complete. Notice we've seen most of the things that are here. The local, the binding, sequencing of instructions, binding to value, an if, a procedure definition, procedure call, a case. Notice the case has only one pattern. If you want to do multiple patterns, you have to nest them. We have values that are numbers or lists. A few other things that we have not yet introduced. The numbers can be either integers or floats. Lists and patterns are of this form, so either nil or some variable or some list-based pattern. So this is the kernel language you've seen up to now. It's almost complete, and we will see the complete one in lesson 4. So now we're going to see the definition of append, and then we'll see its translation into kernel language, and we'll see why this shows that it's tail recursive.